Now let's look at this interface in a little bit more detail. Users and OS. There are two different types of interfaces here. First one is the command interface because few users they pretty much like to have a text-based type of interface. So we have command interface for that, and we have GUI interface. Like in modern Windows or Linux, we'll use a mouse and a pointer to track and to select an option or block and select some components. So we have GUI interface for that. Uh, so let's understand command interface first. Now this is the command interface. We know this command prompt or PowerShell in Windows, right? The moment you open it, a blank screen will be opened, and there will be, let's say, the dollar symbol is the uh, starting of a line, and if you say app one, the CPU will immediately search for this app one in the disk, and it loads the app one into the memory. So now you will have an option to run the programs yourself. So this is command interface. Once this app one is ran, it completed all the tasks that is meant to, and it exits. Once it exits, they again will have another line open. We can call app two or three or whatever. So this command interface, to build this command interface, there are two approaches. Okay, approach. There are two different approaches. First one is built-in command interface. Okay, and the second one is external command interface. Now, what is the difference here? So again, let's say we are going to delete app one. Okay, I'm giving this instruction in the shell. Please delete app one. Uh, I've given this instruction. Now, what happens is this delete command, which is already present inside the command interpreter itself. It is not a different program, and command interpreter, it is not a different program. No, it's not like that. Both are in the same place. Both are packed together. That is a built-in command interpreter. So the command interpreter itself contains the code for each command, right? When you type a command, the shell directly runs it. So there is no interaction there. Just if you enter the delete command, the delete runs automatically. In MS-DOS, the delete command is built into the shell. Okay, you have to give a command like delete file dot text. It'll immediately delete it. Basically, it's like saying the shell has its own brain. Okay, and if the same thing happens in an external command, let's say uh, sh remove file.txt. First of all, the shell has to search for the command which will be in the disk. Okay, somewhere the disk, let's say in bin. It will search for the remove program. It'll take it and it comes back. Now it deletes the file txt. the programs, the commands, okay, they are not uh, actively present inside the shell itself. So here the command interpreter runs separate programs for each command. So shell doesn't have to know how the command works here. It just have to find the command and run the command. So in Unix and Linux, we use this sort of architecture where external command interface is very predominant. And now, why do we use this? So here, the size of the built-in command. Okay, here the size is of the built-in command is, a dep is it depends on the number of instruction, number of commands. Okay, number of commands the shell has. But in external command interface is not like that. The size it depends on it depends on how many programs that are externally made. So the shell is considered as a separate program. The remove command is considered a separate program. If you want to update or add more instructions, this has nothing to do with the shell. If the newly added command has ran into an error, this doesn't affect the shell. But in built-in command interpreter, if there's an error in the command, okay, there's an error in the command, probably the whole shell will be lost. So this sort of separation is a major advantage in external command. Now, we've looked at this diagram and we came to a point where there is a degree of multi-programming. Multiple uh, pro- programs, multiple programs are ran on top of CPU, right? But where we know that multiple programs are running, but where are we getting? Okay, so before that, if if anybody has a doubt, how is multi-programming is better than uni-programming? So, so what I'm saying is, we have the CPU, and there's a particular process. Let's say process P1 is running, and it needs to access the printer. It's called an input and output request to access a printer, and the printer has to print out something. Uh, and after printing it, we are going back to the CPU again to do other calculations. But this sort of job, let's say in execution, if I draw it on a line, it works until here. CPU is working. It waits for some input output request, that is the printer. Again, it starts working. So this part is idle. Idle in the sense there are no computations running in CPU at this moment. So this is sort of a waste of time and resources. If there are other programs that are ready to execute or that are ready to be loaded into the memory, we can do so. So what we have to do, this is a timeline, this is a process one that is running, and here the process one is exiting for input output request. We can put a process two here, and once this is ready, again we can throw this here. So multi-programming will definitely increase the CPU utilization, right? So where all these programs comes from? So we have a disk. This contains a pool of programs. I mean, the pool of programs, they're not sitting somewhere randomly, right? It has a file name, a folder name, a directory. So everything is directory. Everything is properly organized in this disk. This is a disk. So what are these programs waiting for? They are awaiting allocation of memory. Now, who allocates this memory? We have the OS. That will take care of it. And this is the memory. There are pigeonholes in the memory, and we are going to take a program and we are going to put it here. The moment it becomes active, when the program is in memory, it becomes a process. Okay, process 2 and multiple process n. Um, so a process with this, a program in a disk is called a, I mean, the instructions in a disk is called a program, and when that program is loaded into memory, it becomes a process. That is the difference we have to note. So let's say a process is a program in execution. So what I'm going to do is I'm going to restructure a diagram again. So now let's understand this. This hardware, we have OS. Now I'm going to introduce something in the OS. And we have the disk where all the programs will be there, and we have a space to run a program. Okay, so now it's sort of looking like a computer, isn't it? So this is the OS, and we have kernel. For the right now, understand that kernel is the brain of OS. Okay, OS is a broad term. It will handle many things, and kernel is an interface. Okay, that makes the OS to do things. So kernel is like the brain. Okay, brain of OS. Okay, it connects softwares to hardwares. And this new space that I've created here, here a shell is going to run. So what is this shell? Shell is the command interface which we studied earlier between user and OS kernel. Okay, so how does this shell work? We've already seen this. There will be a shell command, and I'm going to call app1. Immediately, what the shell does is it speaks to OS. It tells the OS the certain user is asking for app1, so please find it. Immediately, the OS will search for app1, and it will load into the memory. Now the app1 runs. Let's say the app1 is a browser. So after some time, what happen is uh, this the browser says I'm done. Okay, I'm done. So I'm exiting. Once it exits, we'll come back to shell again. So this is how shell works. Now and kernel, it decides which program gets to use the CPU and for how long. So it tells the OS, okay, this is app one, this is going to run now, and for this long, this is going to run, this is going to utilize the CPU. Again, it's called a burst. Okay, it's called a burst. Now it also hands out memory to programs and make sure they don't mess with each other's space. And there's a program called browser and a program called Spotify. Both are going to run simultaneously on top of OS, but one shouldn't encroach on the memory space of the another. Probably let's say the developers don't trust each other, and they want to have their data safe. So OS has to facilitate an environment for these programs to run. At the same time, it has to be in the most secured way. And the kernel also talks to other devices like printers, peripherals, like that, and it also reads and writes files. Now we have the structure, but they're saying next the developers, let's say people figured out the core part of OS, it should handle the essential stuffs behind the scenes. Okay, the shell, on the other hand, is really just one way for users to interact with system. Now, a good design of OS should be in a way where it is very small. At the same time, it has to be super effective. So, in order to increase or decrease the size of the OS, they try to keep the shell separate and running on top of the kernel. Now the whole setup becomes way more flexible. If there were to be some updates to the shell, it won't crash the OS itself. Now it's not built in to the operating system anymore, and now it's easier to save and update as well. So what I'm going to do is I'm going to restructure again this whole diagram. Um, this is the hardware, and we have OS and kernel. I mean OS is kernel. In the preceding lectures, I'm going to use interchangeably, and the shell. Now this is going to run separately. Hmm? So let's say the shell. You're going to There's a shell command. You're going to call for app1. Once you call for app1, this will exit. App1 will be called from disk, and this will start communicating with the kernel. This is the aforementioned app and OS interface. Right, we've seen somewhere here. We have talked about user and OS. Now we are going to talk about app and OS. So we have a name for this. It's called system calls. Now let's look at system calls in detail. So let's say when a program is in action, okay, and it needs some help from the OS, let's say to open a file from a disk and to read a certain content from file. The process has to call the function which can interact with the kernel, okay, and complete the actions. So this act is called system call. So there's an app, it needs something from the disk, so it speaks with kernel, and the kernel does the thing in turn. So if we have to sort of define system call, it is a request from the program to the OS kernel to perform a low level task on its behalf. All right. Um, so can any program do this? Not really. Not any program can have the access to the hardware. So it needs some privilege, and I'll explain that with an example.